Hi everyone. We'll start now. So we have now come to week number 10, and today we are going to get some insight on one is Frumkin isotherm, and then we can also look into the Warburg based impedance. Okay, so yeah, that's what my plan for today is. Just give me a moment, then I will start. So this week is going to this in the next week I'm aiming to complete up to mass transfer limitation. So then after that, the barber after that you have more of what to say theory based class. You don't have problems. So I think I will be able to complete the porous electrodes and also about the non-linear guys mostly, but that is also small but in the last class. Then finally we'll have a 2 hour session where I'll be giving you a brief summary of what we have seen in this entire class. Right? So yeah, we'll not waste time, we'll start because we have a lot to do. So last week we were looking into assignment number 7, and in that we had questions based on the catalytic reaction. Catalytic reaction is where the absorbed intermediate is not reacting to the product. In fact, it's not getting consumed in the reaction, it just stays. It is facilitating the formation of product. So based on that, we saw numerical problems and like how many number of loops will be coming, etc. based questions we had seen. Find out the rate of the reaction, the current from it, etc. Like how many DC potential is required in order to model it. So such kind of questions we seen in the last class, right? So now we'll move on to the Frumkin isotherm. So till now we were saying the molecules are occupying one layer and we don't see an interaction between the individual molecules, etc. Now, uh, now we're going to look into another type of model which is called the Frumkin model. Okay. So the same thing instead of Langmuir, if you're using Frumkin, how will the modeling be? Okay. So yeah, that's what we're going to look into. We will write the reaction and we'll start the derivation. So I'm taking a simple reaction where M, it reacts, you have the rate constant as K1, it forms M adsorbed and one electron. Now this M adsorbed, it reacts, it goes into solution, and there is also both are electrochemical step. Okay, so we have to also now look into what is Frumkin model? So initially, when we were looking at a Langmuir isotherm, we were like all the sites are equally energetic and the species are equally, all the species that are getting absorbed, they have equal opportunity to see the outside solution, and we don't have any sort of interaction between the adjacent absorbed species. And when they're getting absorbed, all the species on the surface of the metal, they have the equal tendency, all sites are equally active to absorb the metal. So now how is Frumkin model different from this? So here the Frumkin model says that absorbed species, they have the tendency to absorb closer to the previously absorbed species. So that means all the sites do not have equal energy, and that it depends upon where the species are initially getting absorbed, and it just propagates. Like that is what Frumkin isotherm is about. Now, how do we write the uh, the normal mass balance for this one? Here we have M adsorbed species which is getting adsorbed, and we can write the mass balance for that. So how do we write that? Gamma d theta by dt, where I'm saying theta is the fraction of sites which are occupied by the M adsorbed. So in the first reaction, M adsorbed is being formed. So K1 into 1 minus theta is a fraction of sites which is occupied by 1 minus theta is a fraction of sites which is occupied by the metal, because the rest is absorbed by M adsorbed, right? So 1 minus theta is the bare metal, and K1 into 1 minus theta minus. In the next step, you see that the M adsorbed is getting consumed. So you have K2 into theta. This is the normal mass balance expression. Now, how do we write the current equation? It is NF into rate of the reaction. Here, N is 1, and the rate of the expression is from both the expression, because both are electrochemical steps, and becomes K1 1 minus theta plus K2 into theta. Okay, so both these equations are known to us. Now, what is Frumkin absorption isotherm model describe? Frumkin absorption isotherm model, it is describing that the equilibrium constant is dependent, describes that equilibrium constant depends exponentially on the adsorbed sites. Why is this important? Because we already told the adsorbing species have the tendency to get adsorbed on the sites which are closer to the previously adsorbed species. So it says that the equilibrium rate constant, it is dependent exponentially on the adsorbed species sites, which is theta. So it becomes Ki equal to Ki naught exponential Bi into E. So this is already known. This is how we used to write before. This is how. Now, in addition to this, another term will come, which is beta I g theta. Equation 3. Now let's make an assumption. If charged intermediate species M adsorbs, they are repelling each other, we have the what to say, the repelling parameter to be positive. So that we are giving an assumption, or we are just assigning that if charged species, intermediate species, we're talking in specific about the intermediate species, repel each other. In this case, it's M adsorbers. Then intercalating parameter G is positive value. So G becomes a positive value. Otherwise, it's, if they don't repel, they're negative value. So we have the first step. What is the first step? M gives MHR plus one electron, right? And here we are seeing that the first step results in the formation of the adsorbed intermediate. So we can say that the rate constant will be decreasing when the formation of theta, because during the adsorption, the intermediate species, they can repel each other. So it is actually slowing down the reaction as the M adsorbed species keeps on getting formed. So K1 will reduce as the reaction progresses, or as the theta value is increasing. So in that case, the first step beta value will be negative, and in second case, because K2 is because M absorbed is getting consumed, what happens? K2 value will increase and we'll have beta value becoming positive. Okay, if it's not clear, I'll again explain. That is, first step is I'm giving M adsorb plus electron. Okay, so here you see that more and more M adsorb is getting formed. When more and more M adsorb is formed, what happens? Repulsion can happen. So repulsion means it is preventing they can form, they keep on forming the adsorb species, they repel each other. So what is that meaning? K1 should decrease with increase in theta value. So when theta value keeps on increasing, the K1 value should decrease. Okay, and so there will be repulsion happening. Now in this case, what happens? So repulsion is there. This means beta is a negative value. Beta 1 for step 1. This is step 1. Now next step you have M adsorb giving M solution plus electron. So here we see the consumption of M adsorb happening. So this means K2 should increase with decrease in theta. So this means B2 is positive. So first step where M adsorb keeps on forming, it is negative, negative, and when it is getting uh, consumed, it's a positive value. Okay, so that is what it means. Now for any, so this one, right? What did we write? The mass balance. Gamma d theta by dt equal to k1 into 1 minus theta minus k2 into theta. Now steady state. K1 1 minus theta ss minus k2 into theta ss equal to 0. Now what is k1 and k2? K1 equal to k1 naught exponential b1 e dc into exponential b1 into g into theta ss. Same way, okay? So k equal to ki naught exponential bi e gi theta into beta I. So if I'm writing this, this expression becomes ki naught exponential b1 k1 naught EDC because it's steady state exponential beta 1 g theta ss 1 minus theta ss minus k2 naught exponential b2 EDC exponential b2 g theta ss to theta ss equal to 0. So this is a steady state. Now what we can next to do is linearization. So K1 equal to K1 naught exponential B1 EDC plus EAC exponential of beta 1 G theta. Now, how can I linearize it? Otherwise, it is K1 DC into 1 plus B1 EAC. Now, in this case, how will it be? Let's try. K1 0 exponential B1 EDC exponential B1 EAC. Now, you also have exponential B1 G theta SS. Now this remains the same K1 0 into B1 exponential of B1 ADC. So this one we know is K1 DC. Now exponential 1 plus B1 is exponential B1 EAC we can write as 1 plus B1 EAC. Now the same way we can also do the we already know the theta values theta SS plus theta dash EAC, right? So the same thing what we can do is okay. First let us expand it fully and then write it. Okay. So again, K1 naught exponential B1 EDC exponential B1 EAC. Now the same thing what exponential B1 G theta SS. This theta SS term I've just kept it out and we have exponential of beta 1 G theta dash EAC. So now look at this K1 naught exponential of B1 EDC into exponential of B1 G theta SS. What is it? You have it is similar to this expression k equal to k1 ki naught exponential bi into e and exponential g theta beta I. So this is nothing but k1 dc. Now the rest, what to say? I'm going to use different markers just to. Now exponential b1 EAC can be written as 1 plus b1 EAC. Now same way exponential beta 1 g theta dash EAC can be written as 1 plus beta 1 g theta dash EAC. So K1 DC is nothing but K1 naught exponential B1 EDC exponential of beta 1 g theta axis. Okay. So now whatever else is remaining it is K1 DC 1 into 1 plus B1 EAC into 1 plus beta 1 g theta dash EAC. Now I'm simply opening up the bracket and avoid all. Okay, I'll just write it and then show you. K1 DC into 1 plus beta 1 G theta dash EAC plus B1 EAC. And if you see the last term, it becomes B1 EAC, this one. B1 EAC into beta 1 G theta dash EAC. So EAC square is a very small value, we can neglect it. So I'm neglecting that value. This is the value you get for K1. Now similarly, K2 will be K2 DC 1 plus beta 2 G theta dash EAC plus B2 EAC. So this is the expression you get for K1 and K2. Now these two equations are important. Now you need the value for theta dash. You see theta here, theta dash. How do you get theta dash? We know we'll go back to our previous equation, that is mass balance. We know we have to substitute for d theta by dt as j omega gamma theta dash. So same thing we are doing. J omega theta dash EAC equal to k1 into 1 minus theta minus k2 into theta. Now k1 equal to k1 dc 1 plus beta 1 g theta dash EAC plus b1 EAC. Now theta can be written as 1 minus theta dash EAC minus theta SS. Right? This is the first term minus K2 DC 1 plus beta 2 G theta dash EAC plus B2 EAC theta SS plus theta dash EAC. Now simplify it. You have to remove all the terms where EAC square comes, where constants comes. So I'm going to do the simplification. It's better always you try to do it yourself, and then we can cross check the answers, and there are high chances you may end up making mistakes in it. Okay, so I'm going to write it. Gamma j omega theta dash EAC equal to K1 DC 1 minus theta SS plus K1 DC minus theta dash EAC plus K1 DC beta 1 G theta dash EAC 1 minus theta SS plus K1 DC D1 EAC 1 minus theta SS minus K2 DC theta SS minus K2 DC theta dash EAC minus K2 DC EAC beta 2 G theta dash plus B2 to theta SS. So let's remove all the terms where there are only constants. K1 DC into 1 minus theta SS as only constants. K1 DC, D1 EAC, don't know. This term only has constants. K2 DC into theta SS. Yes. The rest all they are all having. So now what next step you can do is you can regroup it so that all the terms with theta dash comes on one side. Okay. It becomes gamma j omega and DC 1 minus beta 1 j. So to SS minus into DC B2 theta SS. Now let's rearrange theta dash equal to K1 DC B1 1 minus theta SS minus K2 DC B2 theta SS J omega gamma plus K1 DC 1 minus beta 1 Z 1 minus theta SS K2 DC beta 2 d theta S. So this is the expression for theta dash only. So basically the steps remain the same except that in the K1 equation there is an additional term of exponential g beta. Uh, yeah, additional term because of that. So now the next step is to write the current expression. So expression we have already written is K1 to 1 minus theta plus K2 theta. So now I'm just gonna substitute everything. Please do it yourself and then we'll cross check. F into K1 DC 1 plus beta 1 G theta dash EAC plus B1 EAC. 1 minus theta SS minus theta dash EAC plus K2 DC 1 plus B2 G theta dash EAC plus B2 EAC theta SS plus theta dash EAC. Now again you have to simplify it and then remove the unwanted one. F K1 DC 1 minus theta SS minus K1 DC theta dash EAC plus K1 DC beta 1 G theta dash EAC 1 minus theta SS. So this what I'm doing, I'm simply removing the bracket K1 DC, I'm multiplying it with 1 minus theta SS, then with theta dash EAC, then again K1 DC to beta G theta dash EAC terms again multiplied by each one. So I'm taking each term and multiplying it and simplifying it. That's it. Nothing else is being done. Plus K2 DC that will G EAC theta SS plus K2 DC B2 EAC theta SS. So this is the expression for IF you're getting. Now you have to remove the unwanted terms and then rearrange it so as to get the IF equation. What all can be removed? The first term can be removed. Then this term can be removed. And now take out IF from it. Sorry, EAC from it. You will get F into K1 DC B1 1 minus theta SS plus beta 1 G 1 minus theta SS theta dash minus theta dash plus K2 DC B2 theta SS plus beta 2 G theta SS theta dash plus theta dash. So into EAC. So this is the expression you get as the correlation between IF and EAC. So it divided by EAC, I'll get the admittance form. The admittance form becoming YF equal to F K1 DC B1 1 minus theta SS plus K2 DC B2 theta SS. So simply I'm rearranging this, okay? So this is the final expression you get it for YF. Simply I have rearranged it and now in this the RT inverse value corresponds to those terms which doesn't have theta dash in it and that is F K1 DC B1 1 minus theta SS plus K2 DC B2 theta 2 SS. This is the RT value. So when you have one adsorbed intermediate, you'll have one loop. But you have been told that there will be an additional loop which is corresponding to the double layer capacitance. So when you have only one adsorbed intermediate, you can have at most two loops where the first one corresponds to the double layer capacitance. So at most two loops means you can have maximum of two loops, but it can also be combined at times, and you can feel it's single loop, and you have only one loop in that case. Okay. So this is how the only difference, in order to account for the interaction between the adsorbed intermediate species, the K1 expression from the previous expression, which is Ki into exponential Vi into potential, that expression is varied a little to account for the interaction, and it becomes exponential G theta I Bi beta I. So where beta is there corresponding to the interaction. So when the adsorbed intermediate keeps on forming, the interaction increases, and in that case, the reduction interaction increases or the repulsion increases. So in that case, beta value is given as negative. On the contrary, when your intermediate adsorbed intermediate gets consumed, the rate of the reaction increases because the repulsion is reducing, because the adsorbed intermediate is getting consumed. So because the interaction reduces, beta value is taken as positive. The repulsion reduces, so beta value is positive. So yeah, this is about the derivation. Now let's look into the questions. So now let's look into the assignment question, which is from problem 7, which we had in the scene. So the first question, it is question number 4. So few questions we had left because we hadn't looked into the Frumkin model. So other questions were discussed in the last class. Okay. Question number 4. A Frumkin isotherm model will reduce to Langmuir isotherm parameter G is. So here you're supposed to tell which is that value for which the Frumkin model will reduce to the Langmuir isotherm. So we already know what is the expression. So where is that Frumkin? How is Frumkin model different from Langmuir model? So when it's Langmuir model, so it is based on the difference the G. You have the K value equal to Ki naught exponential Bi into E. E is the potential. Now when it comes to Frumkin, you have, okay, I've taken the wrong this thing, but still I'll just continue. I'll just write that question and then continue from here. Yeah. You have Ki equal to Ki naught Bi into beta I G theta. So the question is, a Frumkin isotherm model will reduce to isotherm model when the parameter G is. So if you see this part, that is K equal to Ki naught exponential B into potential K naught exponential. This part is remaining the same. in both. So this both will become equal when this term disappears, right? So when will this term disappear? Exponential to what value will give it as 1 as value? So g becomes 0 exponential of 0 theta into 0. This becomes equal to 1. So your g value should be equal to 0 only when this will be reducing to Langmuir isotherm. Because G value is 0 and there's no interaction. So that's a condition. Okay. Now let's go to question number 8. Consider a reaction M becomes K1, MHO plus electron. Okay. Frumkin isotherm is used to describe absorption. Kinetic parameter values. Some kinetic parameter values are given. Okay. So what are the values? K1 naught is given as 10 to the power minus 9 mole centimeters per second. Now B1 10 volt inverse. Then G is 15. Beta 1 is minus 0.5. Now K2 0 10 to the power minus 8 mole centimeters per second. Beta 2 equal to 10 volt inverse. B2 10 volt inverse. Beta 2 equal to 0.5 and gamma equal to 10 to the power minus 8 mole per centimeter square. These very parameters are given, and then finally the question is maximum number of loop that can appear in complex plane plot is what's the answer? This is question number 8. So the parameters are given a lot, but the final question is nothing in that, nothing related to it. It's the maximum number of loops. So when such a question comes, first thing double layer capacitance, you need one loop. Then what you have to check the number of intermediates. So this without any doubt you can write. Next, number of intermediate. And each intermediate corresponds to one loop. So here you have M becoming MHR plus electron. Okay, there is one more step after that, MHR plus, I was just looking, I forgot to write, M solution plus electron. Okay. So two steps and you have only one adsorbed intermediate, so on. So maximum number of loops, this is the sum of this two. So answer is 2. So You can have two loops. You can also get one loop if the values are very close to each other. When you're plotting, you will see only a single loop. So that is also possible. So maximum number of loops are two. Now the next question. So this is actually a continuous question. In above question, in above question, number of electric elements required to model the reaction. Only Faraday part without considering double A capacitor. So we have already seen this type of questions. So from this reaction, only one adsorbed intermediate is there, so you can have only one loop. So basically, when you're plotting, you have solution resistance and one capacitance, and this forms the double layer capacitance, and whatever else comes, this is a ZF. Now, for any one adsorbed intermediate, for every adsorbed intermediate, you need one pair of RC to model the circuit. But this is not that, just that you will also have an additional resistor which is coming because when it's in parallel to a double layer capacitor. So always you have for every adsorbed intermediate you have to calculate one RC. So like how many adsorbed intermediate, those many pairs of RC, and apart from that you will have one additional resistor. So totally the answer will be here one pair of RC plus one resistor. So it becomes totally 3. This is how you have to identify for any circuit, not just for Frumkin, but for any model. This is how you will be finding it. Now, the last question. I'll write in the last page, next page. To model a system with above mechanism, the minimum number of DC potential at which EIS data should be taken is, yeah. So you have an experiment, okay, and you have a model. So in the model, so how many DC potential also you take the data. So if you get something like this in one DC potential, the next DC potential is impedance is like this. Next your DC potential impedance can be something like this or any other. But what I meant is that as this changes, the parameters are C. Okay, those which are needed to model the circuit changes. So that means the value of the parameters keeps on changing when you have data taken at multiple levels at different, I mean, at different conditions. On the contrary, when it's modeled, The model is trying to predict the behavior of this entire system. So the parameters for the model wouldn't change. So for the entire set of data, you will have the same values for the parameters, so the parameters won't change. So, and we know that DC potentials, number of DC potential at which the experiment, the data is collected is such that number of experimental parameters, number of fit parameters. So they're the same thing, if you remember, divided by, and so what I'm talking about is this one. Yeah, this one. Number of DCs should be such that the kinetic parameters are less than or equal to equivalent electric circuit. So number of equivalent electric circuit here. So for this one will require one set of EEC. Now this one will require the next set of equivalent circuit. Although the circuit remains the same, the parameters keeps on changing. Now we know that the number of fit parameters should be number of DC is such that this we had seen in the last class. Kinetic parameters is lesser than the number of equivalent electric circuit. So let's first identify what are the kinetic parameters. So kinetic parameters comes from the model, and these model parameters remain the same for all the different DC potential at which the data is taken. So it will have only one set of model parameters. So we know, let's see, both the steps. So what is the step actually? It is M becoming M adsorb plus electron, and next step M adsorb plus becoming M adsorbed 2 plus electron. So you have K1, K2. Both are electrochemical step. So you will have K1 becomes K1 leaves K1 is nothing but, if it was a normal Langmuir model, you will have Ki naught exponential BE. So this is one parameter. This is one parameter. But this question clearly says to model system with above mechanism. So this is the mechanism given. So this mechanism, it says it's Frumkin. So if it is Frumkin, you will have additional term which is exponential Gi theta I beta I, right? So in this one, the what are the other parameters? Gi is a parameter, beta I is also a parameter. So you will have the kinetic parameters as Ki naught, Bi, Gi naught, and beta I. So these are the parameters. And for any DC potential at which you collect the impedance data, these parameters won't change. Now, when it comes to equivalent electric circuit, at one DC potential, okay, let's first look into how many parameters will equivalent electric circuit have. This we have already seen. That is in this question number. For every adsorbed species, you will have one RC pair. Along with that, one additional R, right? So you have one R coming, and how many adsorbed species here in this reaction? Only one adsorbed species. I have written the reaction wrong. This end solution. So one adsorbed. So one pair of R and C. So it is 3. So we said here that for every DC potential, there will be 3 parameters. For next one, another 3. So this is at one DC potential. So here, kinetic and EEC. For total K naught, Bi, Gi naught, and beta I. Here, for one DC potential, you have 3. Now, number of DC potential is such that the kinetic parameter should either be equal to, Yeah, sorry. So here I have again made a mistake here. So how many kinetic parameters? This is only for step 1. Okay. Now when it comes to step 2, you again have Ki naught. Uh, like, so if I write this Ki naught, K1, B1, G1, B1 for step 1. Now for the next step, you again have K2, B2, G2, beta 2. So totally, so general parameters are K naught, beta I, Gi, and Bi. Right? If it was only a Lamier isotherm, you will have two. That is K naught and Bi. Here you have Gi and beta in addition because it's Frumkin. Every step will have four here because it's electrochemical. Had it been a chemical step, we'll just look into that step once. Okay, I'll just give you the example. If I'm making it complicated, erase everything that I told till now and listen again. You have M giving M adsorbed plus electron and M adsorbed plus becoming M adsorbed, sorry, M solution 2 plus electron. So here, what are the general parameters it will have? Ki naught, B, Bi. Okay, this is one case. Now consider this also case. So in this case, there is one electrochemical and one is chemical. Here both are electrochemical. So what is the expression? Ki equal to Ki naught exponential Bi e into exponential Gi beta I theta. Right? Now, had it been, so this is applicable for an electrochemical step. Had it been a chemical step, we know that it wouldn't vary. That is, it is not dependent on the potential and it's a constant. So in that case, I can write Ki naught or something. It's a constant exponential Gi beta I theta or something like that. So had it been let me write this one. This is 2. So for the step 1, the number of parameters are Ki naught, Bi. Let's not write. I'll write Ki dash. Bi, Gi, beta I. 4. When it comes to a chemical step, what happens? You will not, it is not dependent on the potential, it's a constant. So it has a parameter, something called Ki dash. Okay, it is a constant or Ki. This one, if it is K2, it becomes K2, but it's again dependent upon the interaction. So you will have three parameters. So that's what I was talking. Okay, I hope that point is clear. It is not dependent on the potential when it's a chemical step. Now, in this case, you have two steps and both the steps are chemical. So, for chemical step means it has four parameters. So, step 1 will have four parameters, step 2 will have another four parameters, so total 8. Now, equivalent circuit, one adsorbed intermediate, so you have one pair of RC and an additional R. Had there been two adsorbed intermediate, you have one R, then two pairs of RC to total one R plus R plus RC plus RC. So totally 3R and 2C. Here EEC should be such that how many DC potentials? Such that the kinetic parameters should be lower than or equal to the equivalent electric circuit parameters. So one DC potential can give you three parameters. 3 is lesser than 8. Now if I had taken another DC potential, 2 DC potential, I will have 3 plus 3, 6, which is again lesser than 8. Now let's go for 3 DC. You'll have 3 plus 3 plus 3, which is higher than 8. So the answer for this question is 3 DC potential. I hope that it's clear. It's same as that formula that we did. You can either use a formula also. Find out the number of kinetic parameters. divided it by equivalent circuit and round it up. So here in this question, if I do it, it becomes like kinetic parameter is 8, and here the number of RC is 3. 8 by 3 is 2.6. You have to round it off to higher higher value, so 3. You can either use that or this way. Whichever way you do, this answer you're gonna get. The answer is 3. Okay. So I hope the Langmuir isotherm and the Frumkin isotherm is clear to you. If you have any doubt or regarding this, you can ask me. Now, for today and the next class, we are going to look in deep into what is called the diffusion model. So here you have multiple models to look into, and then we'll be doing the problems, and by next class we'll be winding up the diffusion. And the last class we can look into the porous model and some questions and about the mechanism. So by then we'll be winding up. Then we'll have the last class where we'll be doing about the porous model, what to say, the different nonlinear guys and models like that. Yeah, just give me a moment. So now the next topic is diffusion effects. Okay. So like when the reaction rate is very fast, when the reaction rate is nominal, you have the species coming into a solution. I mean, it's dissolving out, something is getting absorbed. It happens normally. But when the speed of the reaction is very high, large value, the movement of the species will not might not be able to maintain up to that or keep up till that. So what happens? You will have you'll be devoid of the species at the interface. Okay, so there then the mass transfer effects comes to play. So if I say reaction rate is fast, but diffusion of species from or to solution to electrode is slow. So in this case, what happens is diffusion is influencing net reaction rate and current. So when this happens, this will also have an effect on the impedance due to the diffusion behavior. Okay. So now let's consider a case. You have one boundary is that is the electrode surface, which okay. Mm, I'll just draw a figure. Okay. You have the electrode. Okay, this is the electrode, and you have one boundary at the electrode surface. Okay, this is the electrode surface, and you're giving a boundary at x equal to 0. And another boundary is at a finite distance, at some distance. Let's say that is delta. Okay, so any place beyond this point, we say, okay, this one, okay, this place. I am saying that the solution beyond this boundary is assumed to be mixed and of large volume, and in large, because the volume is large, the concentration uniform in the bulk. Okay. In case of RD, okay, so this is called the boundary. So it is in this region, okay, it is in this region where we actually see a diffusion effect coming to play, and you will see that the concentration, there is a gradient or there is a change. So now it is possible to modify or control the region around the electrode, this thickness, okay, this delta. We are able to control the thickness of delta. So this can be done if we are using a rotating electrode where we are rotating it continuously. So there is a convection effect happening. So molecules that are released into the solution are thrown out easily, and you have better mixing of the solution around. So you have the reactants easily available for taking up. So there is a mixing. So in that way, there will be a region boundary layer around the electrode, but that area, will, that thickness of the boundary layer will reduce if we are giving some sort of rotation. So in the case of RD, so RD is nothing but this rotating this electrode. So the bound in the case of RD, we can estimate the boundary layer thickness, and this is done using Levich equation. Levich equation, which says the thickness delta equal to 1.61 into d0 1 by 3. You have the rotational speed omega, which is to the power minus 1 by 2, and you have the kinetic viscosity to the power 1 by 6. Now, there are certain notation, what to say, units for d0 or omega or gamma. You have to use it because by accounting those particular units only, we are getting the value of 1.61. And here in this case, we're solving, your answer will be in centimeter. So unit is important. So when you're increasing the rotation, what will happen? This value. So I hope this formula is clear. Now what if I increase the, you see here, omega is increasing. Gamma is inversely proportional to omega to the power 1 by 2 minus 1 by 2. That is 1 by root omega. So when omega increases, delta will reduce, right? So when I'm increasing the rotational speed, I can say small, small boundary layer. Okay. So if my solution is unstirred, or I can say no stirring, or it's also same as saying it's stationary, the boundary layer thickness, either it can be a finite, some finite value, or it can keep growing and it becomes infinite, which case is called, or that is delta tends to infinity, and this case is called the semi-infinite boundary condition. So these are some of the things you need to understand when you are dealing with the diffusion effects. Okay, so I hope this point is clear. Now we'll be looking into some basics and then we'll look into the derivation. Okay, for electron transfer process, simple electron. So there we saw 404 is an same thing. We are seeing if mass transfer effect comes, how will it be? You have A giving B plus electron forward and backward. Okay. You have something called the Kottke-Levich equation. So till now, when we see, you have one which says 1 by I equal to 1 by due to mass transfer plus 1 by current due to the kinetics. In the previous whatever we looked through this Kottke-Levich equation. We were only considering kinetics, but in actual scenario, mass transfer effects also comes to play, and this is the entire equation you have to consider. Okay. Now for this reaction, A giving B plus electron, the backward reaction is also there. You have IF equal to F into rate. Now when we used to write before, we used to write it as F K1 CA minus K minus 1 CB. And we used to directly take the value of Ca as the concentration of A species reactant. What is the concentration? Concentration of product molecules. But when mass transfer, initially how we used to do is, we used to take Ca equal to Ca1, Cb equal to Cb1. But when mass transfer effects come to play, this is not possible because Ca values are, which is at x equal to 0, which is a interface. At the interface, what is the concentration? And that will be different from the concentration in the bulk. Okay, it's going to be different. So here it will be at x equal to 0 and here also Cb at x equal to 0. Ca at x equal to 0 will be different from the Ca bulk. Similarly, Cb at x equal to 0 can be different from Cb bulk. It depends on how mixed the solution is. Now, similar to what we did, forward reaction will be equal to backward reaction, and we can say K10 Ca bulk equal to K minus 10 Cb bulk. So here you write bulk, but when it comes in the current expression, it is dependent only on the concentration of the product at the interface. K value is Ki naught exponential to power Bi into E. B is alpha NF by RT, and you have B1. B minus 1 is minus 1 minus alpha NF by RT. So these are general expressions we'll be using for solving the problem. We're looking into mass transfer, right? So when you're applying a potential, what happens? Reactant or the react is consumed product is formed. Okay, so and there is a movement of the species, so we are going to call the fixed law of diffusion. That's what I'm writing. This meaning diffusion of species. So here we'll consider flux law. Flux or fixed law of diffusion. So when that happens, dou C A by dou T is equal to dou square C A by dou X square. This is the diffusion coefficient. Dou C by dou T equal to dB dou square. So B by dou X square. Now, steady state, we can say dou by dou T equal to 0. This is important because these expressions are being used if you have to find out CA at x equal to 0, CB at x equal to 0, we can find using this. So just considering the diffusion of species between the interface and the bulk. So we have the concentration of species changes with time as potential changes. So now let's look into what is the difference like when only kinetics is there, when kinetics plus mass transfer come, how it is. Kinetics will always be there. It's that if mass transfer is available or not. So for a single adsorbed species or something, I will observe a graph like this. Okay. So this means RT is equal to RP. Okay. Now, when we are decreasing, when we are applying a positive potential, what happens is both RT and RP will reduce. So if this is at OCP, now if I am applying some positive potential over potential, you can see that this will reduce. So this is what I have told. Now when kinetics plus mass transfer happens, okay, so this for the reaction, like when reaction is happening, how it begins. Now when kinetics plus mass transfer is happening, you wouldn't get a plot like this. Instead, you will can get something different. So getting something different here means that RT is not equal to RP, and when we are positive over potential is applied, what happens is your resistance to charge transfer increases. Why? Because there is the charge transfer becomes difficult when you have when you're devoid of the reactants at the interface or when constant products just clog the surface. So in that case, you will see something like, so you see that the RT value changes. Here the RT value is something like this. And here the value is RT dash is this. So RT value will increase when there is a mass transfer limitation. Now, this is not always the case. Like this one, I've just simplified and drawn. In actual case, it will be something like this is a case when RT is equal to RP. Now, when mass transfer effects come to play, you can expect something like this as the behavior. So it means it does need this after a long time, but something like this. But you will get something like this Warburg 45 degrees. Sometimes it may not need. So this is called semi-infinite boundary condition. And this happens when it is stationary, semi-infinite because it's not actually infinite, but after a long time at very low frequency, it will be muted. So this is all finite. Okay. So this is about how the mass transfer limitation will be affecting the system. Now, when we are plotting a system for a single atom intermediate, you have solution instance, you have the double line capacitance, and some ZF value, okay, which you are using for modeling. This is only when kinetics are there. When kinetics plus mass transfer happens, you can obtain something like this. Here, this one corresponds to kinetics plus mass transfer. Now, let us look at the question we were seeing first. Okay, and that is A given B plus electron. You have K1, you have K minus 1. And here, IF value is equal to K1 CA. Same as before, the only difference is you will not have the CA equal to CA bulk or CB equal to equal, but that is X equal to 0. So you need boundary conditions. So this is the IF equation. Now, at equilibrium, what happens? Forward reaction equal to backward. So K1 dc exponential B1 EDC CA bulk equal to K minus 1 dc exponential B minus 1 EDC CB at bulk. Because it's at equilibrium, these terms cancel out and you have something called K1 dc or K1 naught. I write this K1 naught CA bulk equal to K minus 1 naught CB pulse. And here K1 0. Okay. So this is how your expression will be. Now so there's a first step. You have to write the fixed law. Sorry, current equation. Next step, you write the fixed law of diffusion. Which is dou CA by dou T equal to dA dou square CA by dou X square. And dou CB by dou T is equal to dB dou square CB by dou X square. Now we know at steady state that is doesn't change with time. So if I say that this means and dou CB by dou T also equal to 0. So dou square CA by dou X square equal to 0. Let's integrate it first time. We get dou CA by dou X equal to 0 plus one constant, which I would say as B. for instance. Now again integrate Ca equal to dx plus A. Now you also have dou square Cb by dou x square equal to 0. Integrate it for the first time, you'll get a constant C. Now again if you integrate, you'll get Cx plus D. So these are the expressions. So again, IF can be nothing but F into K1 naught exponential B1 EDC CA at x equal to 0 and at some time minus K minus 1 0 exponential B minus 1 EDC CB at x equal to 0 comma T. Right? This is expression for current. Now we also got the expression CA and CB. Now let's find out the boundary condition. So you have at x equal to delta, which is at the boundary. You have the electrode and this is delta, this is x equal to 0 and x equal to del. So this is a mixed solution. So you have Ca at x equal to del being equal to Ca bulk, or which I can write as Cab. Okay. Now at x equal to 0, you have the species getting dissolved into a solution, and which is dependent upon the rate at which it is getting consumed at the surface of the uh, electrode. So the same thing, if I write it, it becomes dA dou Ca by dou x equal to some t becomes equal to the rate. You apply current and the rate happens. So that one, which is again equal to minus dP, the rate at which the products diffuse out. Diffusion of the product out, I'm taking it as negative. So whichever becomes slower, that is the formation of the product, diffusion of the product, or the diffusion of reactant on the surface. Based on that, that's the lowest step we can identify this. Now, so at the surface, if I write this is also as saying at the surface x equal to 0, I'm saying I know the surface concentration of CA and CB equal to CBS. I have Ca equal to A plus Bx and Cb equal to C plus Dx. X equal to 0, I know what is it. Ca becomes equal to A. And what is the condition at 0? Ca equal to Cas and Cb equal to Cbs. I'll just write it once again. You have Ca equal to Cas. Now what is Ca? You get this from this reaction. A plus B into X is 0. So A equal to Cas. Now same way CB becomes equal to CBS. So do the same thing. C plus D into 0 is CBA. And this means C equal to CBS. Now, we also know the net rate of consumption. What is it? At the surface, you have dA dou Ca by dou X, which is IF by NF, which is the rate at which it is consumed. IF is equal to NF into rate. So I can write rate as IF by NF. That's what I said, the rate at which the product is formed or the reactant is consumed. Now, what is the rate? The rate is K1Ca minus K minus 1 Cb, right? So that is what it is. dA dou Ca by dou X equal to, talking about the net rate of consumption of A. which is equal to K1 dc Ca at x equal to 0 minus K minus 1 dc Cb at x equal to 0. Now we also know that dA dou Ca by dou x equal to minus dB dou Cb by dou x. Now just right, see change in Cs at the surface you will have lesser amount of Ca. So it is Cab which is the bulk which is more. Just change in this and change in the thickness is nothing but del minus dB Cb again and just rearranging it so as to find what is the Cb at the surface. And if you rearrange, you will get Cb bulk plus dA by dB Cab minus Cas. Okay, this is the expression for CBS. So if you have to find out CBS, I need to find out, I know CBB, I know CAB, CAS is the unknown quantity. So from this equation, let us go back to this expression which we have written down. We will use this to find out CAS. Okay, so DA, I'm just writing it again, DA because it's at the surface, CA becomes CAS, CB becomes CBS. Same thing I'm writing. CBS, I can write from this expression. Now let me just rewrite it by opening the bracket. K1 DC CAS minus K minus 1 DC CBB minus K minus 1 DC DA by DB CAB plus minus of minus is getting cancelled, or I'll just write it as I'll just open the bracket, which is better, I think. Okay, you have got this much. Now the next step is to write down all the terms with CAs on one side. And once you rearrange it, which you will have to do it because of time limitation, I'm not doing it. So I will just give you the idea. Take all the terms with CAs on one side, other terms go on that side. Then you will have to multiply it by, you will get something in common, it's DA. You can, what you can do is first you can divide the entire term by dA because dA comes here. Okay, you can just divide it by dA by del, and you'll also have a dB. You can take out the dB also. And once you rearrange it, you get CAS equal to dA CAB by del plus K minus 1 CBB plus dA by dB K minus 1 DC the whole divided by dA by del plus K1 dC plus dA by dB K minus 1 dC. Right? So this is the expression for CAS. So once you find out CAS, you can go back, substitute in this expression. So here what you can do is you can take out you can take out dB, okay, multiplied by divided by dA, get rid of dA, and then when you rearrange, you will get this expression. Now IFDC at steady state then becomes F K1 naught exponential B1 EDC. You know what is CAS, you know what is K minus 1 0 exponent. If a problem is given, then you can find out. Okay, so CAS comes from this expression, CPS comes from this expression, and in case if I say if K1 DC is equal to K minus 1 DC, forward and the backward reaction are the same. In that case, for the problems, okay, you can use this CA bulb equal to CB bulb because the forward and backward reactions are equal. CAS becomes equal to CAB, CBS becomes equal to CBB. So it becomes equal to the bulk concentration. So yeah, based on this, so when it's a steady state, when you have mass transfer limited case, simple mass transfer limited case, this is how you have to solve it. So I think in this one you are not looking for the case where absorbed intermediates are coming. That's a separate case. So where you're just going for the direct reaction type of questions. And yeah, this is an example. Uh, you have A giving B plus electron, you have forward and backward reaction. Everything remains the same. The difference that is no longer the concentration of the bulk is not same as that in the electrode surface. So you have to maintain Ca at x equal to 0 or Cb at x equal to 0, something like that. Then, you know, in that case, there is mass transfer limitation. Fixed law comes in because of the diffusion, and you have dou C dou T equal to dA into dou square CA by dou x square, and dou CB by dou T equal to dB into dou square CB by dou x square. Steady state, you have dou CA by dou T equal to 0, dou CB by dou T equal to 0. Then you can rearrange it, find the expression for CA, CB. Then you need boundary condition. At the interface, you know that it is actually the surface concentration, and to get that, you know, whatever is reacting, that is what. So A is getting consumed, whatever is getting consumed, because that rate corresponds to the consumption of the surface concentration of that particular reactant species. Something is formed, that rate at which it is formed corresponds to the concentration. So that's why the rate is nothing but IF by N. So then at the once you pass the boundary layer, double layer, then you have the CA at that particular after the boundary layer it becomes equal to CA bulk, CAB, same way CB will be CB bulk. So you have the boundary condition at x equal to 0 and x equal to the delta. Substitute, find out. This is the expression for CA, CB. You have to find out, you initially find out the constant A and C. Then you have to find out the term which comes with the length. So you know this expression. Start whatever is consumed, its form. Simplify it. You'll get an expression for how to express the product concentration at the surface in terms of the reactant concentration at the surface. Then when you substitute it back into this expression, consumption is equal to the rate. This is nothing but this IF by NF or the rate. Substitute it, simplify it. Once you simplify it, you will get something in this form. And this is the concentration of the reactant at the surface. Substituted back in this expression, you will get what is CBS. Once you have CAS and CBS, you can then substitute it in the correct expression, which is F into the rate of the expression. And once you substitute, you'll get the rate at the reactant surface. So now the cases when the forward rate constant is equal to backward rate constant. So in that case, you can say the bulk concentration of the reactant equal to bulk concentration of the product. And similarly, at the whatever is the concentration at the surface, it is same as the concentration of the bulk. That means CAS is equal to CAB and CBS becomes equal to CBB. So these are some of the things you have to identify. Finally, what you have to know is what is the formula for CAS, what is the formula for CBS. You need to know the boundary layer condition for such a question. Some kind of derivation comes to you. And then how is IF related and what is the rate of the expression. So these things are needed to know if you have to solve the problem question. So which we'll look in tomorrow's, I mean not tomorrow, next week's class. Before moving on to that, we'll be then looking into, for next class, we'll be looking into two derivations and then immediately moving on with the product, with the questions. One is unsteady state condition. I might not look into the entire derivation because it might not be important for you completely. So I may skip it, but unsteady state expression is needed. So in this case, we said it's a steady state, but what if the time expression is also there? So that is one type. Then the important type, which I will emphasize on, is semi-infinite boundary condition. This infinite condition is important. I think some question is also there based on this in the assignment. So seeing the derivation is equally important. So probably I'll first look into semi-infinite condition, both of them, because questions based on both of them are there in the assignment. And that's also lengthy. Once we finish both of them, we'll look into the assignment question. So the next class is going to be a little lengthy, but with that, we'll wind up that portion. Then we'll look into the porous surface portion. Okay. So I hope today's class was useful and you were able to understand it. Yeah. So that's all for today's class. I am stopping today's class. Okay. Thank you.